Will you do like last time? Just take a look at it and see if it's there. Are you started? I should sit on it. Okay, thanks for your help. Okay, good afternoon everyone. Good afternoon. Good afternoon. Alright, couple of quick announcements. Your papers have been graded. Some of you may have seen it. Please be patient while my graders are uploading your papers. Okay? It will take probably till the end of the day today for them to get it done, but you will be able to see your papers by the end of the day. Right? There is a homework due. It was posted last week Tuesday. Sent out emails as well. Please get on it. Alright, we're going to get going on second order systems. We started this topic last time. This is where the things get a little more complicated. Alright? Second order systems, we started with a spring mass damper example. Equation of motion of a spring mass damper. This was the form that we derived. Mx double dot Cx dot Kx is equal to f of t. Then we had some initial conditions. This is a second order system, so you have two initial conditions, right? X of 0 is x naught. X dot of 0 is V naught. People in the back, can you see my writing? Alright. And then we said that, okay, this is a second order system for a spring mass damper. What if I have a different physical system? How do I come up with a standard form of a second order system so that this is applicable to any kind of a physical system regardless of what it is? Okay? So the equation has to be built on some inherent traits of the system. And the two things that we found out were the damping ratio zeta and then the natural frequency omega n. We did the following. We divided through by the mass. C by m x dot. K by m x is f of t by the mass. Okay. Then we said that k by m, we're going to call it as the square of the natural frequency, and this term C by m, we will do some manipulations to that particular term, which was the following. I divided by omega n, multiplied by omega n, I divided by 2, multiplied by 2, so that I could group together the following set of terms and call them as zeta. So this set here, we called it as zeta. Omega n square is k by m. So zeta is c by 2m omega n. Omega n square is k by m, and so I have a standard representation of a second order system. This f of t divided by m is just a function of time. Just call it as some g of t. Who cares? Okay, it does not really matter. Okay. And so we said that we have the standard second order system as the following. It's x double dot 2 zeta omega n x dot omega n square x is some function of time on the right hand side, and then I have the initial conditions. X of 0 is V. Okay, so what are we going to do now? We're going to spend today and Wednesday probably looking at what I call as the free response of the system. The response of the system in the absence of any forcing functions, or the response of the system in the presence of only initial conditions. Then we will look at the step response of the system, and you will separately look at the ramp response of the system, or response to any arbitrary excitation. Okay? So this way we will be able to categorize first order systems, second order systems, and then we will say at the end of the day, okay, hey, I have a practical physical problem. I will always be able to cast it either as a first or a second order, and I will be able to understand its evolution over time, its behavior as a function of time. Okay, this is why we are doing these things. Alright? So I'm going to start off with free response. Of second order systems. And I'm going to start with the standard form itself, because we know that given a second order system, you can always manipulate it into the standard form. Okay? This is the premise under which we are working. So I start off by looking at the standard form. X double dot 2 zeta omega n x dot omega n square is equal to 0, because this is now a free response under initial conditions. X dot, and I'm sorry, this is x, and then x dot is V. The line of attack is the same thing. Okay, you always have a linear system. This is a strategy you follow. Take Laplace transforms, bring it to the Laplace domain, use certain methods, mostly algebraic methods, partial fraction decomposition or MATLAB. Find out the simplest form of this, and then make use of Laplace tables, take the inverse Laplace, bring it back to the time domain. Why are we doing this? Because we want to understand how the system responds to initial conditions. How does it behave as a function of time if I give it a small knock? That's an initial condition. Okay, so I take the Laplace on both sides, and x double dot Laplace of that is the following: s square x of s minus s times x dot of 0, so that's x naught, minus s times x of 0, which is x naught, and x dot of 0, which is v naught, so that's minus v naught, plus 2 zeta omega n. Those are all terms that do not undergo any Laplace transformation. X dot has the following Laplace transformation: s times x of s minus x of 0, which is x naught, plus omega n square times x of s. Laplace of 0 is 0. Alright, now I take x of s terms, throw the rest of them onto the other side. We've done this manipulation multiple times. So I have x of s square 2 zeta omega n s omega n square. These are all terms containing x of s on the right hand side, left hand side. Then on the right hand side, all the other terms. Okay, so watch this. This is s times x naught plus v naught 2 zeta omega n x naught. Or I can write x of s as that divided by this polynomial is s times x naught v naught by S square 2 zeta omega n s omega n square. Couple of things I want to point out after grading your exam. It is an unforgivable sin to not write a differential equation in the proper form. It is the 8th sin. Okay? So please do not do that again if you have done that in the exam. And I have specifically marked those things out. The standard form of a differential equation is highest derivative first, reduce the order of the derivatives, and then on the right hand side you have things that have nothing to do with the dependent variable. They are all things to do with the inputs. Okay? The second thing is when you talk about the characteristic polynomial, the characteristic polynomial is the polynomial that comes from the free response part of the solution. That's important to understand the distinction. Okay? So once again, characteristic polynomial is this polynomial here that comes from the free response part of the system, not from the forced response. Alright, so this is the characteristic polynomial. Write it somewhere here. And we would like to find the roots of this polynomial. I'm going to squeeze this up here. So roots, let me do it here. S square 2 zeta omega ns the roots of the following. I'm going to go directly to the reduced form. We did this last class. So this is minus zeta omega n plus or minus omega n times square root zeta square minus 1. The factor of 2 cancels off when you do the squaring and dividing it by the factor of 2 and so on. Please know how to get this. This is just basic quadratic equations. Okay? Alright. First things first, stability of the system. Omega n square is always a positive term. So the stability of the system in this situation hinges on the presence of zeta. So if zeta is negative, then what it means is that the real part of the roots will have a positive sign, and so the system is going to have an exponential growth. So a system with zeta which is negative is an unstable system, okay, which is typically physically more or less not possible unless you apply something to the system that makes this behavior in totality a negative value. But if you are applying something to the system besides initial conditions, that's forced response, you don't study stability on forced response. You study stability only on free response, because I can make a system dance to my tunes by doing whatever I want it to do if I'm applying a force on it. Free response means inherently what does the system want to do if I just let it be. In this case, the system does not want to exponentially grow. It wants to either exponentially decay or oscillatorily decay. Okay? Alright, so in this situation, zeta less than 0 is unstable. This is physically more or less not possible. Of course, you can have some special situations where one can manufacture for a material zeta to be negative. That means it's an energy pumping material. Okay, but we will not go into those things. All right. So for us, the system is more or less stable. So zeta for us, zeta is always greater than 0. So the real part of S1, the real part of S2, so the system is stable. So now the behavior of the system, as to what kind of behavior it espouses, depends upon the value of zeta. Is zeta greater than 1? Is zeta equal to 1? Or is zeta less than 1? If zeta is greater than or equal to 1, that term inside the square root bracket is a positive value or a 0 value. But if zeta is less than 1, the term inside becomes an imaginary value. The system behavior appropriately changes. And we are going to look at 3 cases today. Okay, so zeta greater than 1 equal to 1 less than 1. The first case is called as the overdamped case, and you'll see why that is called that way. Overdamped system. So this behavior of the system is very sluggish. Then you have systems that are where zeta is 1, and if zeta is 1, it's called a critically damped system, as many of you know it. The system response in this case is very fast. Then zeta less than 1 is called as an underdamped system or an oscillatory system. This shows oscillations. And this is the fundamental difference between a first and a second order system. A first order system, the free response cannot show oscillations. It is only an exponential growth or an exponential decay. A second order system, on the other hand, its free response has the capability to exhibit oscillatory behavior. Okay, there's a fundamental difference between the two. I'm going to pull this board down. So we're going to look at these three cases. I'm going to call them as case A, B, and C. And different applications have different zeta values. If you're designing a door damper, the door damper actually has a spring inside, so it's a second order system essentially. Your zeta is greater than 1. You don't want the door to slap on your face. But on the other hand, unfortunate bad circumstances, you have to design some kind of a weapon. The recoil system has to have the fastest response. Okay, so that's a critically damped system. If you're designing the suspension of a car, you don't want it to be overdamped or critically damped. You want it to oscillate, bounce a little bit while it decays down. Okay? So those are three practical applications. This is very important stuff. All right. Case A, zeta greater than 1. So if I look at the roots, two roots, S1 minus zeta omega n plus omega n times zeta square minus 1. S2 is minus zeta omega n minus omega n times zeta square minus 1. So there are two roots here. Square root of zeta square minus 1 is always less than zeta. Okay? So note, which tells me that no matter what value of zeta you choose above 1, S1 and S2 are always going to be negative. So I'm going to call them as minus R1 and minus R2. Okay, so they're always going to be negative. So call them as this minus R1. Just rewriting it, you don't need to. And then minus R2, which is they're always less than 0, the totality of it. And so if I look at the characteristic polynomial, S square plus 2 zeta omega ns omega n squared can just be broken into S plus R1 into S plus R2. And what does this tell you? This tells you that there are two distinct real roots. Okay? So they are the two distinct and real roots. Yes.
Can you explain again why you know that they're always negative?
Why is which one?
You said that S1 and S2 will always be negative.
Yes, yes, yes,
Can
of
you
course.
explain that question?
Because, so if I look at theta omega n and theta times, square root of theta square minus 1 times omega n, this term, omega n and omega n are the same. But square root of theta square minus 1 is always less than theta, right? So this is always greater than that, which means that if I come here and if I put a negative sign, then the negative of this is always less than the negative of that, or the positive of that, in the magnitude of it. So you can always think of it as the magnitudes. And so R1 and R2 are always that way. Yep. All right. So if I have this situation, I rewrite my x of s back to the free response. Okay. So I go back to x of s, which was yes, sx naught v naught to theta omega n x naught by okay, this was x of s for us. Now instead of saying this is the term in the denominator, I can replace it by s plus r1 times s plus r2. Okay, so this tells me now that x of s is by s plus r1 and s plus r2. All right. So if that is the case, I can then write this as C1 by S plus R1, C2 by S plus R2. This is your typical standard partial fraction decomposition. So this is we've done innumerable problems of this type. You can find C1 and C2 using either MATLAB, or you can just use the theory of partial fractions. Okay, so C1 and C2 can be found out. Using usual methods. And as we solve an example, it will become more clear, if it is not already. Okay. So system response for case A is the following. So for case A, theta greater than 1, real, this thing to roots. I just have to take the Laplace inverse of that C1 by S plus R1, C2 by S plus R2, and so I get the following. X of t is C1 e to the power minus R1t, C2 e to the power minus R2t. If you want, you can multiply both by the unit step function. But better yet, if you don't want to do that, you can also say the following: the system response is defined only for t greater than or equal to 0. Okay, so you can either multiply it by the unit step function, which means that everything for negative t does not exist, or you can specifically say this is for t greater than or equal to 0. Alright, system response is fairly easy to plot. It's just going to be an exponential decay because it's a stable system. Okay? So x of t versus time. Let me assume positive initial conditions. X naught greater than 0, V naught greater than 0. So I start at a positive value. Time t is equal to 0. At time t is equal to 0, the slope is positive. Okay, so which means that I have a small jump up, and then the system decays down. Okay, so the slope is positive at t is equal to 0. Why is that? Because the initial condition, the velocity is positive at t is equal to 0. So this positive slope is V naught and 1. Alright, so this is case A. We need to do case B and case C. Case B is fairly straightforward too. Case C is the one I want to spend more time on. Any questions so far, please? Fairly straightforward. Just write the characteristic polynomial. We are doing it in terms of symbols, so it might seem a little ungainly, but once you plug in numbers, this just becomes another trivial second order differential equation. Okay, there's nothing funny or fancy about this. Case B is theta is equal to 1. Let me look at the roots of the characteristic equation. S1 is minus theta omega n plus omega n times theta squared minus 1. This is the first root. The second root is likewise minus theta omega n minus theta squared minus 1. If I substitute theta is equal to 1, then 1 square minus 1 is mostly 0. They both cancel off. And so I have both the roots being the same, which is less than 0, which is also less than 0. So this is the case of real and repeated roots. Okay? This is the second situation. So I have real repeated roots. I'm going to call these as 1 by tau, and you will see why I'm calling tau here. What is tau, first of all? Time constant, fantastic, of the first order system. I'm going to call these roots as 1 by tau. Look at the reason for this, and I'll tell it to you later after we complete this. So say S1 is minus 1 by tau is equal to S2. Tau is 1 by zeta omega n. Zeta is dimensionless, fantastic. Omega n has units of 1 by second. So the inverse of omega n has units of time. So this is actually called as a second order time constant. And this is typically referred only when zeta is greater than or equal to 1. Otherwise, you don't call them by this terminology as a second order time constant, because we have other things that help us decide what the system is. Okay, so tau 1 by zeta omega n, so s square plus 2 zeta omega n s omega n square is essentially s plus 1 by tau whole square. Okay, now this is how the system has been decomposed. I'm going to wait for a minute or so. You'll see the reason for why we call it as a time constant, why we call it as tau. Just hang on to it. The units make sense, absolute sense. Okay, they are units of seconds. All right. Let's complete this. Just have to solve. You can immediately recognize that the next exam is going to be slightly more harder, right? Considering what we're doing now. All right. So, x of s, which was s x naught v naught 2 zeta omega n x naught instead of s square plus 2 zeta omega and so on, you just call it as s plus 1 by tau whole square. You have a case of real repeated roots, so we know how to do the partial fraction decomposition. This is C3 s plus 1 by tau, C4 1 by tau whole square. People in the back, can you still see my writing? I'm still surprised because if I sit in the back, I can't. Okay. All right. Obtain C3 and C4 using the usual means. My notes that I'm posting after lecture will have all these calculated in terms of the variables that we solve. I'm not going to waste my time doing that here. Okay, so eventually the system responds. The inverse of the first term, so that's C3 e to the power minus t by tau. Anybody tell me the inverse of the second term? I'll tell you C4 first. Inverse of the second term, the inverse of this particular term here. Yes, yes, yes.
C4 t times e to the negative.
Fantastic, fantastic. So this is the ramp response. All of this multiplied by u of t, or you can say the following. If you don't feel like writing u of t all the time for these kinds of things, you can say instead of the ramp response, this is equivalently C3 plus C4, take the e to the power minus t by tau outside. Ramp response is defined to be equal to t for t greater than or equal to 0. So this is minus t by tau for t. That way. All right, I plot this one. Yes,
Is
question.
there an issue if you write both u of t and t is greater than or equal to 0?
You could, I mean, it's just redundancy. All right, I'm going to plot this. And before I do that, I guess let me first plot it. This is t. This is x of t. I'm going to use the same initial conditions as before. Okay, so x of 0 greater than 0. V naught greater than 0. On the same plot, I'm going to plot two things. I'm going to plot the first case, which was the overdamped case, which was similar to this. Positive slope at t is equal to 0. This is the case of the overdamped response. If I plot the critically damped response for the same initial conditions, this will be much faster, and we'll see why. Okay, so this is going to be the critically damped response. Okay, so I'm going to label them. This is case A, greater than 1. This is theta equal to 1. And whenever somebody plots something like this, the obvious question you should be asking is why? Why is one faster than the other? Okay, so let's take a look at it. And before I go ahead and say that, look at this. This is for a second order system. If I plot a first order system response, free response, I don't have two initial conditions. The first order free response is also an exponential decay for a stable system. The second order overdamped and critically damped responses are also exponential decays for a stable system. And this is why it is pertinent to define this time parameter tau. So that if I have tau defined for any situation, either this case or that case, I can say that the system reaches steady state at 4 times tau. That holds true for both this case and that case because they resemble each other. Okay? The only giveaway here, at least in this situation, is this slope. but I could probably choose a slope that has the same starting conditions as that. Okay, I could have a slope of velocity 0 that would be similar to, pretty much eerily similar to this curve. You would never be able to know the difference. Okay, so the reason for using the time constant, so both of these look similar. So time constant for first order is tau. That is the parameter of the system. Time constant for the second order, for the case of theta greater than or equal to 1 only. Okay, this is the only case where it is useful to define a time constant. It is 1 by theta omega n. And we say system reaches steady state when you have 4 times tau. So steady state conditions are reached. When t is equal to 4 times tau. All right. We have one question to answer. Why is the critically damped faster than the overdamped system? I'm just going to do an order of magnitude analysis. This is by no means rigorous. If you want to be really rigorous, you choose the same initial conditions, you perform a limit analysis. As limit t tends to infinity, which one is faster? Okay, you can do that. I'm not going to do that here. This is just an order of magnitude analysis. So let's say the following. Why case B faster to decay? I write the two solutions down. Okay. So case A, I'm going to have the subscript x suffix a. The full solution is C1 e to the power minus R1t. R1 I'm going to expand as minus theta omega n t plus square root of theta square minus 1 times omega n times t plus C2 minus theta omega nt minus theta square minus 1 omega nt. Okay, this is the solution for system case A. Case B is some C3 plus C4t e to the power minus theta omega nt. Okay, this is the situation for case B. Let's say minus theta omega n plus, that's equal to some magnitude of minus 1. I just choose my parameter such that I get minus 1 as the magnitude. Likewise, minus that is some minus 3. This is obviously going to be a more negative number, right? Because I'm subtracting two things, but in reality adding two negative numbers. Okay? If I add the two, the first and the second, I get from here is equal to minus 2. Does this make sense to everybody? I'm just adding and subtracting stuff. Nothing fancy going on. So I write XA and XB using this order of magnitude analysis. This is just completely order of magnitude, no rigorous reasoning whatsoever. So XA is C1 minus T minus 3T. XB is C3 plus e to the power minus 2T. Case A is when theta is greater than 1. This is equal to 1. So far so good. I have case A, I have case B. I arbitrarily choose some numbers, and I can do that because I can choose these parameters to get these values. I add the first two equations that I write here. I get this minus zeta omega n is minus 2. I write my solutions this way. When time grows larger, the more dominant part of the solution in the first equation is what? It is going to be this guy. This is the one that's going to decay slower. So which means the long-term behavior of the system is going to be affected by the smaller of the exponents. Right? So this is now going to be approximately, as time grows larger, the second situation I can say is more or less going to be dictated by e to the power minus 2t, and you obviously know which one is going to decay faster. Is it e to the power minus t or e to the power minus 2t? It's going to be e to the power minus 2t, which is obviously the case of the critically damped system. So this decays faster. Okay, this is as time increases. And so we can say with, of course this is non-rigorous as I said, but it's reasonable to conclude from this that I can prime my initial conditions, I can choose my initial conditions such that I could probably get rid of this t times c4 quantity and just write it as that. I could choose initial conditions such that I get this term only, and it is quite obvious to see which one is faster. So if you're designing a second order system, and if somebody comes and tells you, I want the fastest response possible for the system, the answer, the one and only answer is a critically damped system. Nothing else. Okay? Alright, so that's the end of this story. I can answer questions as I'm shifting this panel down. I have the last case. And you'll see why these are important is because we're going to solve problems on Wednesday. I can conduct an experiment on a second order system, on some kind of a mechanical system or an electrical system. I can measure certain values and plot the system response based on experiments. And the great thing is if I know that, okay, I can characterize this as a second order system, I can actually recreate the system ODE. If I recreate the system ODE, I am no longer wedded to this experimental setup. I can use that to generalize it to any kind of a setup. So that's what they do in a prototype, right? You have a prototype, you have a small example of the larger system, you perform experiments, you get some data. Using the data, you try to come up with a general predictive model. And that's more powerful than performing experiments every damn time, right? Okay. Last case. This is the most fun of the cases because this can get very complicated very quickly. All right, so case C. In case C, I have zeta less than 0, less than 1, I'm sorry. Look at the roots. And then I have S2 is minus these are the two roots from the beginning. Zeta square minus 1, if zeta is less than 1, is an imaginary number, so I'm going to flip it and say this is the following. Minus zeta omega n plus j times omega n times 1 minus zeta square. Please notice this. I'm taking an imaginary square root of minus 1 out so that the square root of 1 minus zeta square is now a positive value. But I already anticipated that the system response is going to give me complex conjugate roots. And so this is likewise minus zeta omega n minus j times omega n 1 minus theta square, and j is square root of minus 1. Nothing special about writing the j first, you can write it at the end, but this is typically how nomenclature works. Okay? This term, omega n times square root of 1 minus theta square, I'm going to give it a new name. Okay? So call omega n 1 minus theta square as omega d, and this is called the damped natural frequency of the system. The damped natural frequency. You see, this is not an inherent property of the system, because this is dependent on how I select zeta. It's not a natural frequency, it's a pseudo-natural frequency. Okay? And so my roots are the following. And so S1 is minus theta omega n plus j times omega d. S2 is minus theta omega n minus j times omega d. I'm going to write this as the following. So this is minus sigma plus j omega d minus sigma minus j omega d. You can leave it as minus zeta omega n as well, no harm done. This is just making it more easier to write it. I'll get a piece of chalk. Okay, and so the system characteristic polynomial s square 2 zeta omega n s omega n square is s plus theta j omega d We've done this before when we anticipated sines and cosines, when we took the inverse Laplace for complex conjugate roots. Okay, this was done some time back. You have a homework problem that deals with these things as well. If I do the multiplication there, this ends up being s plus sigma whole square omega d whole square. Okay? So that x of s now becomes x naught times s v naught 2 zeta omega n x naught. Instead of the sigma, I'm going to substitute the theta times the omega n. Okay, so this is now going to be s plus theta omega n whole square plus omega d whole square, which I'm going to split and write. Take a brief pause. I have the x naught times s term. I'm going to take that and attach the denominator onto it. So I'm going to have x naught times s by s plus theta omega n square omega d square plus v naught and all these other things, same denominator. What is the trick we are going to use here? Anybody remembers? See, this is the problem with MATLAB. Once you get used to that damn thing, people forget how to do these things by hand.